Hello, my name is Ben Kazules. I'm a rising senior and math major at the United States Air Force Academy, and this is my research video for the 2020 RISS program at Carnegie Mellon University. This summer I worked with Dr. Katya Sakara and PhD student Wenhao Luo in the Swarm Robotics lab on the Robotic Herding problem, where we are tasked to control a group of robots to defend a protected zone from a potentially adversarial robotic swarm using nothing more than collision avoidance. This is the robotic herding problem setup. We have a number of dog robots with which to defend the protected zone. The sheep robots either try to pass through the protected zone or actively attack it. We are able to take advantage of the robotic swarm's collision avoidance algorithms to herd the sheep robots and prevent them from entering the protected zone. This problem has applications to the military, and its solutions can be useful in maintaining protected airspace around military installations or no-fly zones in operational environments. Our task was to develop a simple algorithm and test it through simulation in various different configurations. The algorithm we used has three main parts. The first part prioritizes the sheep robots based on how close they are to the protected zone. The closer the sheep, the higher the priority. The second part assigns the closest available dog robot to each sheep in priority order. This way, the highest priority sheep always have the most effective response possible, while the lowest priority sheep may have to be left alone until they get closer. The third part of the algorithm controls the dog robots to intercept their assigned sheep robots and prevent them from entering the protected zone. These three steps are repeated, and the dog robot's assignments shift between different sheep robots depending on how the situation changes. We ran simulations with a number of different conditions. Here are two example runs, where the simulation on the left has equal numbers of dogs and sheep robots. The run on the right used a formation of sheep robots and a single dog targeting the leader. We also ran simulations with an excess of dog robots, and simulations with an excess of sheep robots. As you can see, the run with equal numbers is a success, as we reach a stable state with the dog robots blocking the sheep robots from entering the protected zone. The results of our experiments show that as long as the number of dog robots is at least equal to the number of sheep robots, they will successfully defend the protected zone. In cases where assumptions can be made about constraints on the sheep robot swarm's movement, or the sheep robots are simply passing through the protected zone, fewer dog robots are necessary, as can be seen in these examples. In the example on the right, we have a formation of sheep robots, and this formation is easily warded off by a single dog robot because of the constraints placed on the sheep robot's movements. In the example on the bottom, we have twice as many sheep robots as dog robots, but since they are passing through, the dog robots are still able to successfully fend them off from the protected zone. The next steps in this work are to further develop and improve the algorithm, and to create proofs of the various results. In addition, it may be possible to explore different tactics from simply intercepting the sheep robots. I'd like to thank my mentors, Dr. Katya Sakara and Wenhao Luo, for all of their time and effort guiding me in this research project. I would also like to thank Carnegie Mellon University and the Robotics Institute, as well as the United States Air Force Academy, for the amazing opportunity. Thank you, and have a good day.